Hello and welcome to my Physics 2212 Lab 5 on Faraday's Law. In this lab, we'll be analyzing visually and modeling computationally a magnet falling down a non-ferrous conductive tube and analyzing Lenz's law and Faraday's law and comparing the results found between the observational and computational models. Faraday's law is the idea that the integral over a closed boundary of the electric field it will be equal to the negative of the change in flux over time of that field. This creates an electrical force in the opposite direction to the change of flux as a result of the electric field created in the opposite direction. This gives that the prediction is that the magnet will fall through the moving tube should experience a force in the opposite direction, which should slow down its fall compared to just gravity acting on the magnet. In the experiment visually, the magnet can be seen falling down the tube. When the north pole was facing down, the velocity of the magnet was greatly reduced. The average time that took to fall was 2.6 seconds. Footage will follow. The next portion of the experiment is the computational experiment, in which we are computationally modeling an aluminum conducting tube and a magnet falling through Python code on GlowScript. The first step is to create the aluminum conducting tube, which is given in the starter kit. The next step is to input conditions and to use the Lab 3 magnetic dipole function and recreate it here to use later. The next step is to create the magnetic flux function of the induced current. This can be found through analyzing the lecture 43. The next step is the creation of the simulation loop, finding the gravitational force acting on the magnet and to calculate the magnetic force acting on the magnet of the current in the tube. The last step is to calculate the magnetic field at each ring and then sum the forces, which will allow you to calculate the velocity and position functions in relation to time. The time found in the computational model is 4.889 seconds, which is larger than the time found in the visual model. The difference between the computational model time and the visual model time indicates some discrepancy between the two and can be further analyzed in the following discussion questions. As indicated in the final output picture of the system, the red and blue colors indicate current flowing in the opposite direction. The blue color indicates a clockwise current and a red color indicates a counterclockwise current. This is because the red current will be the induced current, which will have an electric field that will be opposite to the change in flux in time, which will be opposite to the north magnetic field, which will mean that the electric field will have to flow upwards into the magnet, indicating a counter current flow. Also of note, if you flip the magnet around and have the south end facing down, the same thing will happen through the system as the induced electric field will counter the change in flux over time, and therefore we will still see the exact same resistance to the magnet's motion. The time of the real-world visual model was slower than the time necessary for the magnet to fall through the tube in the computational system. This could be because the computational system uses an ideal case, while in the real-world version, as noted in the video, the magnet is not fully vertical when it falls down, and there's some interaction between it and the side of the tube. And in addition, the aluminum foil is not completely dense, and therefore there will be some small discrepancies in induced field. The shape of the velocity versus time plot tells us that throughout the entire system, gravity is acting on the magnet. However, when it is inside of the tube, there is an upward directional force that is constant, that is acting in opposite to the velocity of the magnet. If the resistivity of the conductor were reduced as close as possible to zero, this would cause for no magnetic force to be in the opposite direction as the magnet falls through the tube. This would be similar to what you would see a magnet falling through a plastic tube in which only the force of gravity acts on it. This is because the electromagnetic force is equal to the current over resistance. So if there is no resistance, then there could be no electromagnetic force, and therefore there would be no force acting in the opposite direction. If holes or slots were cut into the tube, this would not affect the current system in the model. This is because that there would still be a change in flux over time, which would still induce a negative result in flux, which would still cause the same induced current and subsequent force in the opposite direction.